Howdy, Rock Buds. It's Rock Papa. Hope you guys are doing fantastic wherever you are. Grammy and I appear at Balsam Mountain in the Smokies, 5,000 feet above sea level, staying cool. But today I thought we would talk about limestones, the limestones of the Appalachian Foreland Basin. We're going to talk about 4 different limestones deposits. We're going to talk about when they were deposited and how. We're going to take a look at some pictures of these limestones. We'll talk about thin bedding versus thick bedding. We'll talk about mineralization and karst topography for these limestones. So stay tuned. And if you like this video and it's helpful, please subscribe. Thank you so much to my wonderful subscribers. I think about you all the time and I really do appreciate you. So here we go with the limestones of the Appalachian Foreland Basin. This limestone story is going to be a tale of 4 limestones, actually. The first one is Precambrian rift-associated limestone, which is now marble. Our second limestone is Cambrian rift-to-drift limestone, and we'll talk about what rift-to-drift means. Our number 3 limestone is Ordovician taconic orogeny limestone. And at number 4, we have Mississippian period Allegheny orogeny limestone. Hey, Rock Buds, technically speaking, the first 2 limestones aren't really part of the Appalachian Foreland Basin, but they are very close and they preceded the formation of the Appalachian Foreland Basin, so I'm going to include them in there. So first, let's talk about our Precambrian limestone, which is now marble. This limestone was deposited in the late Precambrian period, before 550 million years ago. And by the way, capital M-A means million years ago, or mega annum. This limestone was deposited as supercontinent Rodinia was beginning to rift apart. After the limestone was deposited, subsequent orogenies metamorphosed it into marble, and you can find this marble in the Western Blue Ridge Geologic Province. And this map shows you the Western Blue Ridge Province. It's the bright red area and the darker red and the yellow inside of this bright red area. The yellow, by the way, is Great Smoky Mountains National Park. Here are some local names of this marble that runs all up and down the eastern United States. So how did this happen? This funky picture shows Rodinia supercontinent just beginning to rift apart. You can see 2 rift basins that are filled with rift sediments. These rift basins will become the Western Blue Ridge Province eventually. As the continent edge sank, a carbonate bank developed on top of the rift basin closest to the ocean. So what is a carbonate bank? Well, picture the Great Barrier Reef off of Australia. It's full of creatures that incorporate calcium carbonate in their shell structures. All these calcium carbonate rich shells settle down on the bottom and are mashed into a limey ooze that later becomes limestone. And then later on, the taconic orogeny, the Acadian orogeny, and finally the Allegheny or Alleghenian orogeny, when Africa crashed, metamorphosed this limestone into marble. The limestone, pictured yellow here, along with associated sediments, was pushed up into a very tight syncline by these orogenies. And erosion created this layer cake kind of display, which results in 2 stripes of each deposit along the surface of the land. Okay, on this geologic map of Georgia, see those 2 really thin, purpley lines running through Ellijay, Jasper, etc. That is the Murphy Marble Belt. Each of the lines represents an edge of the marble deposit that was pushed into a syncline. This marble deposit, called by many different names, runs all up the eastern United States. Here's a picture of marble, and you can see by that fizzy business that it will fizz in a strong acid. Here's some marble tiles from a marble quarry that kind of hint at the different kind of colors that you can get in marble. And here's what a marble quarry looks like, and that little orange thing is a big old excavator. As you know, marble makes great statues. Here's Michelangelo's David. Okay, now it's time to look at our number 2 limestone, which is actually limestone, and that's the Cambrian Rift-to-Drift limestone. The Cambrian Rift-to-Drift limestone was laid down during the Cambrian period between about 530 and 500 million years ago. This was during the time right after Rodinia supercontinent rifted apart. This was a very exciting time called the Cambrian explosion of life, where myriads of soft-bodied creatures appeared suddenly in geologic time in the warm, shallow oceans surrounding the rifted continents. And where do you go to see this Cambrian limestone? Well, you go to the Valley and Ridge province. And here are some local names for this Cambrian Rift-to-Drift limestone. So what the heck is rift-to-drift? Hey Rock Buzz, before we can talk about rift-to-drift, we need to ask ourselves, why do the edges of the continents sink down after a supercontinent rifts? Well, there are a couple of reasons I can think of. First of all, before a supercontinent rifts, there's a huge amount of heat underneath it that's going to eventually rift it apart. That heat bulges the continent up. So in that case, the sea level goes down or the edge of the supercontinent comes up. After rifting occurs, that heat from underneath in the mantle is no longer there, and so the continent pieces sink back down. Another reason is that rifting creates oceans, and oceans are made by the massive production of basalt lava on the ocean floor. And that's just like one of my grandkids jumping into the bathtub. When he gets into the bathtub, the water level in the bathtub rises up to compensate for the volume of his little body in there. And now that we know that the edge of North America continent sank down, or the ocean rose up after Rodinia rifted, let's look at Cambrian Rift-to-Drift. Here is another funky drawing in which the light blue is the sky, the dark blue is the ocean, and the maroon color is the edge of the continent. You can see the orange layer of sand that represents the sand of the coastal plain and the sandy beaches. A little further out in the ocean, we find a layer of dark mud that comes from the mud of the intercoastal waterway and from rivers that dump mud into the ocean. And then a little further out still, in say 300 feet or less of water, you have all kinds of reefs and shell creatures whose bodies fall down to the bottom, creating a limey or lime-rich ooze that will become limestone. This is generally what it looks like around the edges of all continents in climates where shell creatures and coral reefs can flourish. As the edge of the continent sinks and the sea rises, the sand beaches and coastal plain sands migrate uphill. The dark mud rises up to cover the old coastal plain and sand beaches that are now underwater. And the limey mud, which will become limestone, covers the dark mud. This whole process continues, and eventually the whole package is raised up above sea level by an orogeny, so that you eventually end up with a layer of sandstone covered by a layer of shale, covered by a layer of limestone, and this whole package can cover thousands of square miles of land. That is the rift-to-drift process, and that's how our Cambrian limestone was formed. The yellow line on this map follows the Valley and Ridge province where you can find this Cambrian rift-to-drift limestone. And here's just another view of the Valley and Ridge province, which is located between the blue Cumberland Plateau on the left and the reddish Western Blue Ridge geologic province on the right. We're talking about places like the Great Valley of Georgia, the Shenandoah Valley of Virginia, and other valleys all up and down the eastern United States where the limestone has weathered into super productive rich soils which have provided outstanding hunting and agricultural opportunities since prehistoric times. Here's some Cambrian rift-to-drift limestone and a couple of things to notice about this. First of all, we have a lot of thin layers of limestone, one on top of each other. That's called thin-bedded limestone. The thin layers tell us that this limestone more than likely formed fairly close to the shore in an area where the ocean was actively moving back and forth. The second thing is that the lighter color of this limestone tells us that it's made mostly of dolomite, which forms when magnesium in seawater combines chemically with the limestone to form magnesium calcium carbonate, or dolomite. Here's a sample of Copper Ridge dolomite that comprises a large portion of the Cambrian rift-to-drift limestone. The key thing to remember here is that unlike the other limestones that we'll look at, Cambrian limestone has a whole bunch of dolomite in it. Dolomite won't fizz as readily as limestone or marble, but if you scratch it up good with a knife, then you can get a pretty good fizz off of it. Trilobites first appeared in Cambrian shale and Cambrian limestone. In this picture, the pink is the Cambrian rift-to-drift limestone. This is the taconic orogeny, and the taconic volcanic island arc is pushing down on the edge of the continent, and that's forcing this limestone up above sea level. Three things happened. First, a bunch of sea creatures died in an extinction event when their habitat was pushed up above the water. Then rainwater, which is a weak acid, made all kinds of caves in this limestone deposit and created what's called karst topography. Then hot volcanic fluids from the taconic orogeny pumped valuable metals into the openings in the limestone. This is called mineralization. This is a hunk of zinc ore that was pumped into the Cambrian rift-to-drift limestone in the Knoxville, Tennessee area, producing a zinc mining industry. Now let's take a look at limestone number 3, the Ordovician taconic limestone. This limestone was laid down in the taconic orogeny foreland basin during the Ordovician period, which lasted from 500 to 450 million years ago. You can find Ordovician limestone today in the Valley and Ridge province and in the Nashville Basin. Here are some of the many local names for this Ordovician limestone. Ordovician limestone is generally dark gray, and it's a fairly pure limestone without any dolomite in it. It's thick-bedded in some places, thin-bedded in others, and it does have minor inclusions of chert. In this familiar picture of the taconic orogeny, which of course occurred all up and down eastern North America, you can see the word foreland basin. That formed when the volcanic island chain on the right pushed the continent edge down as it approached and created this foreland basin, or forebasin for short. Our Ordovician limestone formed in this forebasin. During the Acadian and Alleghenian orogenies, this limestone was pushed up into folds and faulted, and later erosion removed all the top levels, creating valleys in the Valley and Ridge Province that were rich in limestone. In this picture, the pink is the Ordovician limestone, and the yellow line marks the present-day ground surface after millions of years of erosion. And again, the yellow line shows you where the Valley and Ridge Province and the Ordovician limestone can be found. However, Ordovician limestone can also be found around Nashville, Tennessee, in the Nashville Basin, where erosion has removed all of the layers that were on top of it. Here's some Chickamauga limestone that you can find in the eastern part of the Taconic Foreland Basin. You can see it is pretty thick bedded. And this tells us that this limestone was formed in relatively deep, quiet water over a long period of time. And here's some Stones River Ordovician limestone that you can find just east of Nashville, and you can see that it has some thin beds in it. And here's some more Ordovician limestone called the Carter's Limestone, a few miles east of Lebanon, Tennessee. Right in the middle of the Carter's limestone is this dark layer, and it's really cool because it's made of bentonite. Can you guess where it came from? That's right. The volcanoes associated with the Taconic Island arc were puking out volcanic ash like crazy, and the wind was blowing it into the Foreland Basin where this Ordovician limestone was forming. Eventually, the ash formed into bentonite, which is a very sticky clay. Here's a sample of Ordovician limestone that they call Tennessee marble, and they make it into all kinds of things. This is a piece of tile. It's really limestone from the Holston Formation southeast of Knoxville, Tennessee, but it has these fantastically pretty bryozoan fossils in it that give it a marble-like appearance, and so they market it as Tennessee marble. Here are some important Ordovician limestone fossils. Okay, rock buds, now it's time for us to take a look at number 4 and last limestone, Mississippian Alleghenian orogeny limestone. Our Mississippian limestone was laid down in the Alleghenian orogeny Foreland Basin. The Mississippian period lasted from about 350 million years ago to 330 million years ago. And you can find Mississippian limestone around the Western Highland Rim, in and around Clarksville, Tennessee, and at the base of the Cumberland Plateau. Think Cumberland Gap National Park. In the Western Highland Rim around Clarksville, Tennessee and vicinity, the Mississippian limestone is white and tan in color, and it's extremely cherty. As a matter of fact, it's mostly chert, and it's also fossiliferous. That's hard to say. East of the Western Highland Rim, and also at the base of the Cumberland Plateau, it can be dark gray and both thick and thin bedded with minimal chert. Here we have Africa crashing into ancient North America. It's pushing down on the land crust, creating a massive foreland basin. Mississippian limestone is forming in shallow parts of this basin. The Himalayan-sized Alleghenian front mountains erode. All of the limestone is covered with a thick layer of sand, which creates a massive coastal plain. Over the eons, much of this sandstone layer erodes, exposing the Mississippian limestone in places like Clarksville, Tennessee on the Western Highland Rim and at the base of the Cumberland Plateau. I collected these specimens of the St. Louis and Warsaw limestone when I was visiting my sister in Clarksville, Tennessee, part of the Western Highland Rim. I tested all these specimens with acid, no fizz. That means they're almost entirely chert. I did find some bits of fossilized crinoid in these rocks, though. Nature's symmetry is beautiful. Here's some Mississippian St. Louis limestone showing both thick and thin bedding. Possibly the thin bedding is when the limestone formed near the shore where the waves were active, and the thicker bedded happened as the sea rose and things got quiet. Here is some Warsaw limestone of Mississippian age. And here's some Mississippian Bangor limestone from the base of the Cumberland Plateau. I find very little chert in this. And this map just shows you where you can find the Bangor limestone at the base of the Cumberland Plateau in Georgia. Mississippian period fossils for your viewing enjoyment. Hey Rock Buds, believe it or not, we finally reached the end of the line for the limestones of the Appalachian Foreland Basin. Thank you so much for hanging in here with me. And hopefully you liked this and it was useful. Please subscribe. And this here is your Rock Papa saying to all my most excellent rock buds, happy rock hunting. Papa out.